times. So I apologize in advance if people have seen at least part of it before. I'll try to highlight, because this is going to be a talk on like old-ish results and more modern results. So I'll try to highlight the new things, but I want to give kind of the full picture and the full story. So for those who have seen some of these talks, I hope you find something new at the end. Okay, so this is going to be um, based on joint works with Jashi, who is my graduate student at Princeton, and she's actually graduating tomorrow. So she's defending her thesis tomorrow, and she'll go to MIT as a postdoc. And Yao Yao, who is at Singapore, and her former student Jamin Park, who is now my postdoc at the University of Barcelona. Okay, so this is based on some collaboration that we started a few years ago while both of our graduate students were starting, and it has continued up until today. Okay, so this is a kind of a long journey over a bunch of years, and this is pretty much where we're at. There is also some connection with some previous talks at the seminar, and yeah, this is kind of I don't know, like an interesting topic that has picked up recently. So, in a rough way, today I'm going to talk about the Euler, to the Euler, incompressible to the Euler equations, and specifically about the question on rigidity and flexibility. Okay, and I will explain in a bit what I mean by that. Okay, so maybe in this seminar, this the 2D Euler equation doesn't need doesn't need an introduction. So I'm going to abuse notation. This is coming from the fact that we're more used to call, so theta is going to be omega, but because of notational reasons and historical reasons for us, since we embedded to the Euler in a class of other equations, we call it theta, but pretend that, I mean, theta is going to be the vorticity. Okay, so in 2D, theta is a scalar, omega is a scalar, and it's transported by an incompressible velocity. So u can be written as the grad perp of a string function psi, and then the relation between the scalar theta and the string function psi is via the Laplacian. Okay, so this is known to everyone here. We can recover the solution u as a singular integral. Okay. So throughout this talk, I'm going to work, or I'm going to be focusing mostly in two settings. And if I'm not, then I will explicitly say so. There are a bunch of slides on some other setting, but mostly I will consider omega, the vorticity, to be either a smooth function, and then I will say that I'm in the smooth setting, or a step function, or a patch function, or a patch setting, or a patch-like solution. Okay, so theta is going to be either a nice smooth function with the appropriate decay at infinity. I'm not going to be worrying about that, or a collection of characteristic functions of some domains. Okay, so if I look at the patch problems, or the vortex patch problems, the nice thing is that now I can decouple, and I can write the evolution of the boundary. So if the vorticity is, let's say, equal to 1 inside, 0 outside, just to fix ideas, then I can track the evolution of these type of solutions based only on the evolution of the boundary. So this is nice, because this gives me an advantage, because it's a 1D problem. So it's not a 2D problem anymore. Then I only care about the evolution of the points on the boundary, which are like z of alpha t. Okay, and then these points on the boundary move along in the normal direction given by this velocity via the singular integral. Okay, so this is known as the contour dynamics formulation, and it's quite helpful because now, especially for like numerical purposes, for example, this reduces the dimension from 2 to 1. So one can play around, turn on the computer, see what happens, see what's going on, and maybe prove some theorems. Okay, so there is no problem from the point of view of the existence of solutions by Udovic's theorem. Everything is nice, and the patch keeps being a patch for all time. And many years ago, there was a conjecture whether there could be a finite intersection of the boundary in a finite time self-intersection of the boundary. Okay, so this was raised, um, and there was some numerics that suggested that, but Sheman and a little later Bertozzi Constantin proved that if you start in C1 gamma, so if your interface, the regularity of the free boundary is C1 gamma, then you stay in that class C1 gamma for all time. Okay, so then yeah. Okay, so today I'm going to be focusing on stationary and for a little while uniformly rotating solutions. Okay, so I will now explain what I mean by stationary solution. If I'm a smooth stationary solution, then the partial t of theta is equal to 0. And we have this condition here. And I'm going to say that I have a uniformly rotating solution with some angular velocity, capital omega, if in the rotating frame, the solution is stationary. Okay, so if I subtract the rotation, then I have this equation here, and I can rewrite it as this form. So grad perp of f, this f is going to be important later on, times nabla theta is equal to 0. Okay, and due to this characterization, we can see that for each connected component of a level set of theta, then this f has to be constant. Okay, so that's fine. But the main obstacle or the main technical disadvantage is that this constant may change from component to component. So if everything is simply connected, then life is good. But if we were to have, let's say, even in the patch setting, if we had like two characteristic functions, then f is equal to c1 here, and f is equal to c2 here, and we don't know if c1 is equal to c2. And this poses a technical problem when it comes to prove certain results, because they use moving plane methods, and then the moving plane methods fail whenever these two constants are not the same. Okay, so this is for the patch. I drew two patches here, but you can imagine the same sort of condition in the smooth case by just looking at the level or at the super level sets of the scale. Okay,
sorry, what
so
is kernel K? K, what is K?
K is the Newtonian potential. K is the Newtonian potential.
Thank you.
Yeah, sorry about that. Thanks a lot for the question. Okay, so a very easy observation, and this can be extracted from the equations, is that if we start with radial data, then this is a stationary solution. Or it can also be checked that this is uniformly rotating with any angular velocity. Okay, so this is very easy to check, but the main question that we are making ourselves here is the converse. Okay, so can we characterize all uniformly rotating solutions? Can we characterize all stationary solutions? And in particular, do these rigid solutions have to be radial? Let's say under some assumptions like decay or compact support or something like that. So this is kind of the main question that we were making ourselves when we started working on this. And yeah, numerics sort of seem to suggest that this was true, but it's not easy to prove it. Okay, so Frenkel, for in the stationary case, assuming that the patch was simply connected, and again using moving plane methods. In fact, all three of these use moving plane methods. prove that indeed that's the case. So there is rigidity. Any solution which is stationary and is simply connected as a vortex patch, then it can only be a disk. Okay, MIDI extended these results by assuming a little bit more on the shape of the patch that here I summarize by writing D convex. It's not quite that, it's a little less restrictive, but the assumption is quite long technically. So in the case where the angular velocity is negative, he was able to prove the same. And using a clever trick, in the case omega equals 1/2, he was also able to conclude the rigidity. Okay, and lately there have been a bunch of papers, one by Amel and Nadirashvili in puncture domains, in annuli, or in planes without a point, using under some extra hypothesis in U, they were able to settle also the rigidity question for omega is equal to 0. And there are a couple of papers by Konstantin Drivas and Ginsberg in periodic channels or perturbations of periodic channels where the rigid solution is a shear. And there is a preprint, and as far as I know, some work in progress as well by David Ruiz and Pier Alberto Sigbaldi, who I believe also gave a talk here on just very, very recent results on the same problem or related questions.
Sorry,
okay.
What is the difference between positive omega and negative omega?
It's the speed, whether you rotate counterclockwise or clockwise.
But the theorems are different.
Yes, I mean, I'm assuming here that the vorticity is a characteristic function. So if the vorticity is a characteristic function of a set, then this induces somehow rotation in one direction.
Mm-hmm.
Okay, so if you look at this from the point of view of the fluid. So it is natural to, of course, if I change the sign of omega, then the sign of little omega, the sign of big omega is also going to change. But here I'm assuming so far that this is how it looks like for a certain D. Okay, and then it may be natural that one direction is preferred to the other. I mean, it's not obvious, but one may think as to why omega positive or omega negative may be different a priori, and in fact they are.
Thank you.
Okay. Okay, so this is when it comes to rigidity, flexibility. There is a family of explicit solutions constructed by Kirchhoff that are ellipses. So if you take an ellipse, you evolve it by 2D Euler, then this is a rotating solution. This is a uniformly rotating solution. One can compute the velocity, the angular velocity explicitly, and it gets this formula. A and B are the semi-axes, and depending on the ratio of A and B, one can get an angular velocity which is between 0 and 1/4. Okay, so other than that, are there more? And the answer is yes. So in the 70s, in the late 70s, Diem and Savusky constructed numerically bifurcating from disks, non-trivial, meaning non-radial rotating solutions for 2D. Okay, so the point is that there may be other things that are not disks, that are not ellipses, that rotate for a certain angular velocity. Oops. Okay, and there are more. So these are secondary bifurcations. This branch corresponds here to the disk. This corresponds to the ellipse. Threefold, fourfold, as the figures that we saw before. But there are even secondary bifurcations on the elliptical branch. Okay, so these are numerical calculations done by Kam in his PhD thesis. And again, I stress out the dates because by then it was not known whether there could be finite time singularities or not for this problem. So people were interested into finding non-trivial examples of solutions for which there was global existence. Okay, so that's the motivation. And at the end of the branch, many, like some bad things could happen. And in particular, it is believed that there are singular solutions at the end of the bifurcation branch. These are numerics. This is not known. And it is believed that these solutions, of course, these are steady. There is no time evolution here, but they develop corners at the endpoints of these piecewise solutions. Okay, Elgindi and Jong have constructed other singular solutions that also have some corners, but they are not these ones. Okay, and the families are actually quite rich. There are changes of topology, for example, so we can see that if we follow the single vortex family, we end up in this limiting state, which seems to be also attained by following the two vortex family. Okay, so what I'm trying to convey here is that the family of rotating solutions is not as rigid as one may think of just by looking at like the trivial ones like disk or the ellipse. In fact, there is a big zoo of solutions. Now, what do all these solutions have in common? Well, let me first say a little bit what people have proved. So far, everything that I showed were numerics. Burbia in 82, using local bifurcation theory, he proved that at these values of omega, which I can write as 1/2 minus 1 over 2m, there is bifurcation. So if I look at omega and then let's say r, then there are certain things bifurcating at certain values of omega, and there is an accumulation point at 1/2. Okay, so Burbia proved that one can apply a local bifurcation theorem, and at these values of omega, there are non-trivial solutions. And later, Midi, Mateo, and Verdera showed that the boundary of these patches is infinity. And myself, together with Angel Castro and Diego Cordova, we showed that it's indeed analytic. We proved the existence of these secondary bifurcations of CAM. And there's another paper by Hassainia, Masmoudi, and Wheeler where they do global bifurcation results, and these are all just local. And they can extend these branches. There is a recent paper by Berti, Hassainia, and Masmoudi where they construct quasi-periodic tori close to the ellipses for certain aspect ratios, and many more results by other people, some of which are in the audience, like Claudia Garcia, Ludovic Godard, Zina Hassainia, Tufik Midi, Francisco de la Hoz, Joan Mateu, Coralie Renault, Émeric Roulet, Juan Soler, and Joan Verdera. And I hope I'm not missing anyone, but if I'm doing so, please forgive me.
Sorry, Javier.
Yes.
These are bifurcations from what again? Because
from the disk.
From the disk.
Yes.
And M means.
M means the symmetry class that you're taking. So
the symmetry class. Okay.
So M is the M-fold solution.
Okay.
And then if you assume you are in the class of M-fold, then you will bifurcate at a certain angular velocity.
Okay. Thanks.
So here is what we proved. We showed that if you take omega to be smaller or equal than 0 or greater or equal than 1/2, then there is nothing else. So this is a strong rigidity result, and this is summarized in the figure that I drew here. So before us, it's in black, and after us, it's in red. So before us, it was known, like more or less what I summarized. Anything at 0 simply connected, or at 1/2, anything simply connected has to be a disk. And if you're below 0, if you're convex, you have to be a disk. But we're not assuming anything about the topology of the solution. This also works with minor modifications for the smooth case. Okay, so I'm stating here for the patches, but in fact we can prove a similar statement in the class of smooth solutions. And the proof uses calculus of variations techniques as opposed to like previous proofs that were using moving planes. Okay, so this is where we can take advantage of this and sort of overcome this obstruction of the F that I mentioned before being possibly different constants on the different components. Okay, so I'm doing pretty badly on time. I'm going to keep moving a little faster. Okay, so the proof, I'm going to sort of summarize, it's a short proof. If we take this energy fractional and we compute the variation, the first variation, we evolve the density rho to be driven by this velocity v, which we are free to pick. Then the first variation of the energy is simply this term v dot grad f. Okay, so what we want to do here is to pick the v in a way that on the one hand we get that I is 0 and that we get that I is non-zero. Okay, so that would be our goal. The first the first restriction or the first condition that we're going to put on V is that V is incompressible. If V is, let's say, smooth enough that we are able to integrate by parts and V is incompressible, and we use that F is constant on the boundary. Here, for the sake of simplicity, I'm assuming that the boundary only has one piece, but later I will explain how to drop that assumption. Then it's easy to see that we can get that I is 0 just by integrating by parts, putting the F from the boundary term outside, which is constant, and then integrating by parts again. So so far so good, I is 0. And now but we haven't really used anything about V. So let's use things about V. Okay, so ideally, I would like that if my patch is something like this, I would like to make it more radial. I would like to pick a V in a way that it becomes more radial. So my ideal V would be minus X. Okay, so that would be my dream V, but the problem is that this is not divergence free. Okay, so instead of picking this V, I'm going to pick the closest V to this vector field in the space of divergence free vector fields. Okay, and this is given by this P, which is the correction. So V is going to be minus the gradient of some potential phi, which is given by x squared over 2. This creates the minus x term. And then there is the correction, the projection onto the divergence free vector fields given by P. And P satisfies the equation that I wrote down. Okay, so phi is harmonic. This will imply that V is divergence free. And as I said, the intuition behind this field is to pick the closest one from the space of divergence free vector fields to minus x. Okay, now if we do that for that particular V and we substitute back, then after simple calculations, symmetrizing and keeping the rotation term, we end up that the first term is equal to 1 over 4 pi, the area of the patch square, minus the rotation pi. Okay, so here there is nothing really too fancy about it. So this solves I1. If I go to I2, integrate by parts, and move the gradient from P onto F, then we are left with just this quantity, this integral of P. So what we really need to compare is this integral of P versus the second moment of the patch and some some constraint or some extra term coming from the area. Okay, so if omega is 0, means that this term is not here and this term is not here, then we need to compare simply the integral of P with the area of T. But this is a kind of isoperimetric inequality that was proved by Talenti, and in fact he proved literally the equation that we need. So by using talented result, then we can sorry, then we can already extract a sign out of I, and this will contradict the fact that I had to be 0 in the first place, unless it is a disk. Okay, so I is strictly positive if the patch is not a disk, and this gives the contradiction, that that we're looking for. And if omega, so this solves the case where omega is 0. If omega is if omega is smaller than 0 or bigger than 1/2, then we can use that the second moment is a maximizer or a minimizer, depending on the sign of omega, and we can get a similar inequality, and we can extract the sign of I even in those cases. Okay, so that's a short summary of how we do it. Now, how to go from simply connected to multiply connected. If the patch is not simply connected, then the danger is that the F may take different values on each component of the boundary. So we're going to impose this condition on each piece of the boundary. And to do so, we're going to keep the same D as before, and we're going to modify the P in a way that the P is equal to some constants that have to do with the area of the holes enclosed by the pieces of the boundary of D, and then adapt talent disproof to this case where we can have holes, and we can prove the same thing. So if omega is smaller or equal than 0 or greater than 1/2, in this more complicated multiply connected setup, the same thing holds true. Okay. In the smooth case, we can sort of imagine that the smooth case is a limiting case of lots of layers. We can sort of discretize our smooth function as a sum of many patches, and what we try is to apply the previous theorem, do quantitative estimates depending on the number of patches that we put, send that number to infinity, and arrive to a contradiction. Okay, so this is what makes the paper to be quite long, and this is the main technical difficulty, but we can still do it. Okay, so assuming that the vorticity is non-negative and let's say compactly supported, then we can prove similar results for omega smaller or equal than 0. Okay, and the technique is what I said. So we derive quantitative versions of the case that I described before, and approximate our smooth function by n layers, and send n to infinity. Okay, so we did some results for the vortex sheet, but let me skip those. And I'm going to focus now on the flexibility case, which is a paper that we posted in December of last year. So we were wondering whether the condition that I just saw before, namely that omega has to be positive, is actually necessary or not. Or in other words, if we drop that condition, can we find non-trivial, non-radial stationary solution? So is this a technical thing, or are there things whenever we allow the vorticity to change signs that are non-trivial stationary solution? Okay, so that's the question that we did ourselves, and the answer is yes. So there is flexibility, and in fact we can construct some vorticities which are sign changing and non-radial, also locally non-radial, meaning that we are not allowed to cheat by putting just two circles in a way that they don't talk to each other. I mean, of course, this is non-radial, but this is cheating. So this is what I mean by locally non-radial, with finite energy, and in a way that this is a stationary solution. Okay, so the solutions that we are going to construct are of patch type. There are going to be sums of certain layers. The boundary of these layers is going to be analytic, and the whole thing is going to be close to an annular profile with vorticity of different signs. Okay, so one thing you may wonder is, well, can you do this by perturbing point vortices and then the singularized point vortices? And the answer is certainly not in an easy way. If we are looking for finite energy solutions, and I will explain it in the next slide, why that's a problem. So there is a paper by Musso, Packard, and Wei, where they constructed finite energy solutions that don't have compact support, and our solutions are far from point vortices, and they do have compact support both in velocity and in vorticity. Okay, and the proof is going to use Nash-Moser scheme because the standard bifurcation theorems are not going to be available for our setting. Okay, now let me go back to this observation of what happens if you start close to point vortices. So if you start close to point vortices and you try to construct things with finite energy, the problem is that your candidates are going to be just the trivial ones. So if you take point vortices solution, let's say a bunch of point vortices with circulations theta I, then if you have a stationary solution, then the vortex angular momentum is 0. So this cross product, this product, the sum of products of the circulations is 0. And if I also impose that the point vortex has finite energy, then the sum is 0. But in fact, the combination of these two conditions already implies that all the thetas have to be 0. Okay, so this is bad because then we would have to perturb from 0, and that's a problem. Okay, so we cannot just find a configuration, a point vortex configuration with finite energy, and then somehow desingularize the point vortex in some way. Okay, so we're going to work in this abstract framework. So we're going to, as I said, assume that the vorticity is going to be some constant times a characteristic function of some domain, BI, and we're going to work in the either 2-layer or 3-layer setting. So we're going to find a multi-layer solution. Of course, this is a trivial solution because everything is radial if I put annuli, but the hope is that by perturbing these circles, we can find a non-trivial one. Okay, and we're going to use one of the thetas as a parameter, and we will use some of the other variables to cancel the scalings, and in some cases also to work with finite energy spaces. Okay, so in an abstract way, we want to find a 0 of some function where R is the parametrization of our boundaries, and theta is one of the constants. So we're going to have essentially like 4 parameters: b1, b2, theta2, and theta1, minus the ones that we take out to kill the symmetries. Okay, and the function that we want to find the 0 is the normal velocity along the boundary components of all the layers. Okay, so this is what we do. So let's warm up and look at the 2-layer case. So if we have 2 layers, let's say we normalize things so that the outer layer here is 1, the inner is b. This I'm going to call it theta, and here I'm going to put -1. So then this is also where we started. So if we take 2 layers, then this is how the vorticity looks like. It's the superposition of these two disks, and then everything is nice. Everything looks good, and we look at the operator, and the operator diagonalizes if we do Fourier in the angle. So if we do Fourier in the angle, then life is pretty good. We can diagonalize everything mode by mode, and this is how our operator looks like. So just to fix ideas, pretend that this is 0 and pretend that this is 0 because they are nonetheless exponentially small. So this is the place where one has to be looking at. And this is what is going to be the problematic part, which is the outer boundary. Okay, so if we do it like this without really thinking too much, we try to to find something non-trivial in the kernel. Remember that we have a trivial solution given by the disk. We want to bifurcate, so we want to find something non-trivial in the kernel of this DF. Then essentially what we are aiming to solve is some value of theta that makes this determinant equal to 0. Okay, and we can do that. This is a quadratic equation, so we can do that. So another thing that we should notice is that df loses one derivative as long as theta is not 1, because we have minus n and then times b squared over 2, b squared minus theta, okay, plus ta, ta, ta. And here again there is another term which is order n. Okay, so so df, if we look at it in Fourier, loses one derivatives, f loses one derivatives, f is the nonlinear part, df is the linearization around the annulus, but they both map the starting space into the target space. So that's good. As I said, for any n, we can solve the quadratic equation coming from the determinant, and we find a non-trivial solution that leads to a one-dimensional kernel of df. Okay. Now, for those solutions, theta is strictly bigger than b squared. So the solutions that we find will not have zero mean. The integral of the vorticity will be strictly positive. So this is a problem if we were to find to look for finite energy solutions. Now, if we forget about that, then we can use a Krandall-Rabinovich argument. We can do bifurcation using or Lyapunov-Schmidt or your favorite way of calling it. And we can construct a branch of solutions emanating from the disk. So we have like the disk, and then there is at some point in theta, then there is something going out, and this is all local. Okay, so there are many of these. If we are free to change b, so if we change b, we can find solutions with arbitrarily small negative part. But the question here is what happens if we look for solutions with finite energy. So if we substitute, that would imply that theta is b squared. So this is a problem here because now this term becomes 0. And then we start having problems in the sense that the linear operator df doesn't map hk plus 1 into hk anymore. Okay, so now the matrix or the linear operator doesn't lose the right amount of derivatives, and this is a problem. So at this point, we were wondering, well, this is because of being two-layer. Is this because of the base solution being radial? Maybe we can change these two things, and maybe we can find something else. Maybe this is just a technicality coming from the simple setup that we are taking. Okay, so for quite some time, we thought that something like this could work, and in fact, this is a really long calculation, and we just figured that it wouldn't work. Well, we had done it, and we were at the very end. So this is probably something that happens. So our idea was the following: go to 3 layers, and then find values of theta for which the vorticity has negative average for some values, and then positive average for some other values, and prove that in fact there is a connection. There is a connection of solutions connecting this branch with this branch. Okay, and numerically, this looked pretty clear, and we were seeing these connections between these two branches, and one can find values of the parameters for which this thing happens. Now, the problem is that this doesn't work. We could never get the argument to close because our estimates, sort of as we progressed along this branch, they degenerated, and we weren't really able to sort of close the two branches, although numerically it seemed pretty clear. Okay, so we were kind of disappointed, but we learned something. We learned something through this. So the problem, and this is a real problem, that argument will never work. So the problem is that the velocity, as before, as when we were looking at solutions that didn't have zero mean, then from the fact that they don't have zero mean, there is a contribution to the tangential velocity. Okay, and then through that contribution of the tangential velocity, there is a contribution to the diagonal elements of this matrix Pm. One can see that that this has a contribution, and thus, if the energy is finite, then these constant terms, this 1 minus theta square or whatever it is in the matrix df will not be there. So then then our operator df is not going to match, is not going to lose the right amount of derivatives. So so there is no way that this approach will work, because then df and f will not be at the same level. They will not lose the same amount of derivatives, and then we are in trouble. Okay, and this holds no matter where we are perturbing at. So if we were to perturb from a more complicated thing that had finite energy, we will still run into this problem, and there is no way to get out. Okay, so that's bad, and this is due to this lemma, which for a while we thought it was easy, and somebody probably would have known about this. And we look at the literature, we ask a lot of people, and nobody seemed to know about this. And we were surprised, because the proof is very short. It's elementary, I would say, but we hadn't seen this in the literature before. So what the lemma says is that if you take a vorticity, which is, say, compactly supported, just to fix ideas, this is not the greatest generality that one can prove it. And we look at the exterior domain. So this is omega, the exterior domain of where omega is supported. And we have finite energy and stationary solution. So F is constant on the boundary of omega. So F, the boundary of omega, is constant. Then F is constant in omega. And this is going to imply that U is 0 in omega. In other words, if vorticity and velocity having compact support for stationary solutions with finite energy are equivalent conditions. So if U or omega are stationary solutions of Euler, compactly supported and finite energy, then U compactly supported is equivalent to omega compactly supported. Of course, one is trivial, but the other one was something that we weren't aware of and we couldn't find. So this is this is what really creates the problematic part. And the proof is a maximum principle argument. So I'm going to walk over this quickly, but essentially this follows a maximum principle type of argument. Okay, so you can check it. This is not very difficult, but it's new, and this was sort of surprising for us. Now, consequences. As I said, this is not something specific of the trivial solutions. So if we were to find a non-trivial solution near a trivial one, we will not be able to use any kind of implicit function theorem because the operator, the linearized operator, will fail to be an isomorphism because it's not going to map the same amount of derivatives as the nonlinear operator. Okay, now the hope is that one can do an Nash-Moser argument and 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 overcome this difference in loss of derivatives between the linear and the nonlinear part. Okay, so what's the framework going to be? As I said, 2 layers, no chance. So we're going to work in a 3-layer framework. Again, the system is diagonal. Everything looks good, but now the blocks are 3 by 3, so it takes quite some calculation power. We will use some of the free parameters as our disposal to kill off all the symmetries and force zero mean, and then work in a space where we just have finite energy, and we have enough parameters. There is enough flexibility, and we can find values of theta for which the determinant that I showed before is 0. So this is not a problem. Finding the bifurcation is not really a problem. The problem here is how to deal with the regularity mismatch. Okay. So we're going to construct a new functional G such that dg satisfies all the spectral conditions as in df, and we now reformulate our problem into finding a 0 of this new operator gs. Okay, so if we find a 0 of g tilde s, then we are done, and then we win. So what we will do is ideally, we would like to do a Newton method for GS. Okay, so this is kind of the first idea that comes to mind. So update our guess for R as the previous guess minus this condition here, and start, let's say, from 0. So in order for this to work, we would need a very good guess initially, and then the invertibility of this operator dg. But everywhere, not just at 0, not just at the bifurcation point. So we really need to understand the inverse of this dg at essentially a small ball close to the annular profile. Okay, and this is tough because as we know now, dg is not invertible. So what we do is we decompose dg as 2 operators. So one that vanishes but loses the right at the solution, but loses the right amount of derivatives, and one that loses one more derivative, one less derivative, but that we understand well. Okay, so we are we are really splitting the contribution coming from the part of the operator that vanishes when we are at a solution, and the part that doesn't. Okay, now the main idea is that we don't really need to know the full invertibility of dg. We just need what is called an approximate inverse, namely an inverse at the solution, and with satisfying some good estimates away from the solution. But we don't really need the full inverse, exact inverse at any point in the space. So we just need to understand the inverse very well at the solution, and understand it reasonably well close to the solution. And this is enough. This is enough for our purpose, because we just have to understand the part of dg coming from this capital A. So the part of the little a, we can just, I mean, not throw it away, but it's good enough that since it goes to 0 as we approach the solution, it will not really matter in the scheme. So there is a loss of derivatives, and thus at every step we apply some regularization operator Sn, and due to the quadratic convergence of the method, then this scheme will converge fast enough, and it will yield a solution in the end. Okay, so this is more or less how we construct the solutions, and let me stop here. Thank you very much for your attention.